So, in this presentation, I'm going to talk about local protection for LDP-based label switch paths. The central idea is topology-independent local protection. In a sense, the solution provides local protection in any topology as long as there is an alternate path in the network that avoids the failed network resource such as link and node. So today, many service providers deploy LDP to establish transport LSPs in their network. These transport LSPs are confined to single IGP routing domain. The services that rely on these transport LSPs depends on the connectivity. That is, these transport LSPs provide connectivity to the services. Therefore, any failure in the network result in disruption of the services. Clearly, we need to minimize the service disruption, and to minimize the service disruption, we need to minimize the connectivity disruption. To minimize the connectivity disruption, we want to rely on the faster route technology because that is the fastest way. Clearly, in any network, there will be both link and node failure, and the faster route scheme needs to cover both link and node failures. It's totally unreasonable for a faster route scheme to constrain the network topology. Service providers should not design their network topology to accommodate a particular faster route scheme. It should be the other way around. The faster route scheme should be able to accommodate any topology. Therefore, the solution needs to provide topology-independent local protection. Additionally, we want to minimize the configuration required. We want to ease the configuration required to deploy this solution. And finally, the solution should rely on the existing IETF standard. Why? Because we have enough machinery in the existing IETF standard to design such a solution. In the rest of the presentation, I'm going to talk about how to accomplish these requirements. So let's talk about building blocks that are necessary for TIFRR, the point of local repair. It's a node which notices the failure of downstream link and node and begins forwarding traffic towards the merge point using the bypass LSP. The next building block is the merge point. Any router on a LDP-based LSP, provided the path from that router to the egress of the LSP is not affected by the failure of link and node. Now we've seen a point of local repair and merge point. Let's talk about the next building block, the bypass LSP. A LSP which is established from the PLR to the merge point. The LSP is established prior to the failure. This presentation assumes the use of RSVP-TE protocol to establish such LSP. And finally, we need to obtain the label mapping from the merge point. The label mappings need to obtain prior to the failure. Once the PLR detects the failure, it swaps the incoming label with the label from the merge point instead of the label from the next hop. TIFRR provides both link and node protection. So let's talk about link protection. So 2 slides back, I talked about the building blocks. This is an example of how those building blocks are used to provide link protection. So in this topology, let's consider a LDP LSP from R1 to R7 via R2 and R3. Further, let's focus on a protected link between R1 and R2. To protect this link, a green bypass LSP is established from R1 to R2 via R4, avoiding the protected link. Now, the label mappings are same as prior to the failure because the merge point is the next hop. The R2 is a next hop for the PLR R1 in this case. The same bypass LSP is used to protect all the LDP LSPs that traverse from R1 to R2. So the number of bypass LSPs is completely independent of the number of LDP LSPs protected. All the alleged problem of RSVP-T scalability pretty much do not apply in this scenario, because the number of link protecting bypass LSPs is equal to the number of links in a network. Therefore, the RSVP-T scalability problem are just a red herring for this scenario. So this is a figure which illustrates the working example of link protection. So for a LDP LSP from R1 to R7, which is indicated via the red arrows, the labels are signaled in the reverse direction, which is indicated via the light blue arrows. Also, to protect a link between R1 and R2, a green bypass LSP is signaled from R1 to R4 to R2. In the steady state, the traffic flows from R1 to R7 via R2, R3. In the event of a link failure, R1 begins forwarding traffic on the green bypass LSP towards R2 via R4, and this is done for all the LDP LSPs that traverse the protected link R1 to R2. And this helps to restore the traffic in 50 milliseconds, which enables us to restore the connectivity in sub 50 milliseconds, which further enables service restoration in sub 50 milliseconds. So in the beginning of the presentation, I talked about one of the goals as reducing the configuration required. There has been a long-standing perception that we need to configure each of these link protecting bypass LSPs manually. These perceptions make it very complicated for the service provider to deploy the solution. Clearly, any additional configuration is extra burden for them. Let's see what we can do. So it's just a single line configuration under Junos. So all those long-term perceptions are just a perception. So let's talk about node protection now. So what needs to be done prior to the node failure? This is not a whole new thing, and it has the same building blocks, and they pretty much iterate the same way. The PLR is same as a link protection, which is a router which is one hop upstream to the protected node. The merge point is a little different because the merge point is not the next hop in node protection case. The bypass LSP is similar to link protection, except that it is signaled from PLR to the merge point, avoiding the protected node instead of a protected link. The label mappings are different. Look, now the question is, how many more label mappings does the PLR needs to maintain? To reduce the number of label mappings, the merge point should flood only the facts which are corresponding to all the loopback addresses of all the routers in a network to the PLR. To improvise it even further, the PLR should obtain the label mapping from the merge point on demand, rather than letting the merge point flood all its label mapping to the PLR. And further, the merge point itself does not need to acquire any label mappings. So the total number of label mappings the PLR needs to maintain is twice and nothing more. Now, in last few months, we have received a lot of questions on TLDP unscalability. Now, it's necessary to understand when TLDP doesn't scale. It doesn't scale when you have large number of facts advertised over a large number of TLDP sessions. If you just advertise what is necessary on the TLDP session, it does scale. Now, let's use the same example that we use in the link protection case to determine the merge point. So, in this topology, let's consider a LDP LSP from R1 to R7. Further, suppose we want to protect the node R2. With respect to R2 and with respect to this LSP, R1 is a PLR, which is one hop upstream of the protected node, and R3, which is next hop from the PLR, is the merge point. Now, when R2 is not an ABR, we can determine the next hop. The R1 can determine the next hop R3 based upon its SPF computation in the same SPF. If we contrast this with LFA and remote LFA, they do multiple SPF computations on the PLR and still do not provide 100% coverage. Now, this is the last missing piece in determining the merge point. How to determine the merge point when the protected node is a ABR? Now, in this topology, consider a LDP LSP from R1 to R9 via R2, R3 and R7. Now, R3 is a ABR. If we want to protect the ABR, the PLR, which is R2, cannot determine the next hop R7 as a byproduct of its SPF, because R2 and R7 are in different areas. They are not on the shortest path tree. So, in such a scenario, R2 can determine the merge point as an alternative ABR. The alternative ABR is determined from the IGP database. Again, as we seen in case of not ABR example, the discovery of alternative ABR doesn't need any computation. You can just figure it out from your IGP database. Just as we seen what it takes to enable link protection, let's now see what it takes to enable node protection. So right now, let's talk about the node protection example, the working example of node protection. So in the steady state, the traffic flows from R1 to R7 via R2 and R3. A green bypass LSP is established from R1 to R3 via R4, avoiding the protected node. And in the event of node failure, R1 begins forwarding traffic on the green bypass LSP to R3, avoiding the protected node. The green bypass LSP is used to protect all the LDP LSPs that traverse the PLR, the protected node, and the merge point. And what is the configuration required to enable node protection? Again, it's a single line configuration, and everything else that is required to enable node protection, such as TLDP sessions and the node protecting bypass LSPs, are signaled automatically in Junos. So this is how we make it very easy for the service providers to deploy the solution. Now, service providers who deploy LDP to establish both unicast and P2MP LSPs can use the same mechanism for protection. We pretty much use the same targeted session and the bypass LSPs to obtain the label mapping and tunnel the traffic to the merge point. So, in summary, in the beginning of presentation, we laid out the requirements, and now let's see how we have managed to accomplish those requirements. The solution provides link and node protection for LDP based transport LSPs using RSVPT bypasses. The RSVPT bypasses can be traffic engineered using variety of constraints. It places no restriction on the network topology. That is, it provides topology independent local protection. If we contrast this with LFA and remote LFA, it places certain restriction, they place a certain restriction on the network topology and thus do not provide 100% coverage. The additional provisioning and configuration required can be fairly small. It totally depends upon the implementation, but in GNOS, it's just a single line configuration. And what is required to make this solution work, like TLDP sessions and the bypass LSPs are signaled automatically. The solution relies on the existing IETF standards. It uses the RSUPTE for establishing the bypass LSPs and TLDP for obtaining the label mapping. The same solution is used to provide protection for both unicast and P2MP LSPs. Now, the solution has same inefficiencies that Kirti talked about in the ring topologies. And for the ring topology, we need to use the solution that he described yesterday. The link protection has been available in GNOS since 12.3. The node protection is available starting 15.2. We have a demo code running of TIFRR, so if you want to see TIFRR in action, please visit our booth. We have a plan to submit this solution to the IETF probably on Monday, and this brings me to the end of presentation.
Thank you, Santosh. Any questions? Well, thanks very much.
Thank you.
So our next presenter is Linda Dunn.